Today we will be discussing the topic radioactivity from AS level physics. The phenomena radioactivity was widely used in studying about the structure of atom in beginning of 20th century. And the chapter starts with the famous experiment carried out by Rutherford, alpha scattering experiment. From your exam point of view, you need to understand the result of the experiment, said experiment, and how we can interpret that. So all of you know alpha scattering experiment from your IGCSE. Alpha particles from a radioactive source was bombarded to a thin gold foil, and it was observed that most of these alpha particles went straight through the sheet without any deflection at all. Few got deflected, and very few got a deflection of 180-degree or backscattering happened. So what could be the cause for this, and how do we interpret this? Since we had a large number of undeflected alpha particle, we can conclude that atom is mostly empty. And since we have a few backscattered alpha particles, we can conclude that mass is concentrated in a very tiny space, a very small region, nucleus. In fact, it is about 10 to the power minus 15 meter small. And the nuclear density is so high, all the matter of the atom is concentrated, or almost all the matter is concentrated in this tiny little region. Now, the nucleus has positive charge. How do we get to know that? It is because alpha particle is basically helium nucleus, and it has two positive charge. So if a positive charge is deflecting, then you should have another positive charge from where it is deflecting, concluding that nucleus has a positive charge. Moving forward, we get introduced to the notation that we use to denote a nucleus, and it usually is like this. Let's say you have the element X, and here we denote Z atomic number, and atomic number is essentially number of protons itself. Then you have mass number A, which is the number of protons plus number of neutrons. For instance, if you take like a uranium atom 92, 235, this 92 indicates the number of protons. 235 indicates number of protons plus neutrons, that is 92 plus 143 gives you 235. And these kind of questions appear in for 1 mark. Now, the nucleus, as I mentioned, it's a very tiny region of order of 10 to the power minus 15 meter. Let's say you consider uranium atom. It has 92 protons, okay? And these 92 protons are fit into this tiny little region. And you know that protons have positive charge. If they have same charge or like charge, then it has to repel. But atom is essentially stable. Of course, some more stable than others. But how does this happen if there is electrostatic repulsion? So there is a stronger force which overcomes this electrostatic repulsion, which acts in a very short range. We call that as strong nuclear force. Now, for this atom, you can have the same atom with different mass number. We call those type of atoms as isotopes. For instance, you can have uranium 92 to 38. One of the common ones that you will see is the three isotopes of hydrogen. S11, we call it as protium. H12 deuterium, and S13 tritium. As you can see, protium, it has atomic number 1, meaning its number of protons is 1. And since its mass number is also 1, we can conclude that it has 1 proton and 0 neutron. Deuterium, you have atomic number same, P is equal to 1, number of protons 1. Since you have mass number 2 and 1 proton already, so the number of neutron it has is 1. Similarly for tritium, proton again 1, number of neutrons is going to be 2. The next topic, which is relatively new to you guys, is particle physics. Ever since we looked inside atom, we came to know that it is made of different building blocks, and we eventually came to know about protons, neutrons, and electrons actually way before that. Now, when investigated further, it was theoretically proposed that these protons and neutrons could be made from even more fundamental particles. The protons and neutrons, they are not, they cannot be called fundamental particles. There are certain particles that make up these protons, neutrons, and other particles that you are familiar with. In 1950s, we discovered something called quark, and it comes in 6 flavors. They are named up quark, down, charm, top, bottom, and strange. And these quarks have charges. For instance, U quark or up quark has 2/3 charge of an electron. Similarly, if you look at D, it is going to be -1/3. These are the ones that is very important for you guys. Now, what you see here on the screen is called standard model of universe, and you can see 6 flavored quarks, and we have their anti-quarks also. Anti-quarks or anti-particle in general has the same mass, opposite charge, and a lot of other properties that you will see later. Now, there are other fundamental particles as well. We call them as leptons, and you already know one of it. These 6 leptons, first one being electron, you already know. Then we have muon and tau. And there are other particles called neutrinos, and electron has electron neutrino, muon neutrino, you have tau neutrino. And these neutrinos are actually particles with a very small mass, tiny little mass, that exist like all over the universe, penetrating our bodies, and it is surrounding us actually. So these are the fundamental building blocks of matter, quarks and electrons. Now, you also have force carrying particles that you don't have to worry about for the time being. So these particles, these fundamental particles, quarks and leptons, they combine to form other particles that you're familiar with. For instance, you take quarks and you make material or matter using these quarks. Obviously, you are not doing it, you are not doing anything. It happens automatically. And let's say if the matter is made of quarks, we call them as hadrons. They are affected by strong nuclear force. Now, if you have a particle that is made of 3 quarks, we call it as a baryon. One example is proton, another is neutron. And the composition, quark composition of proton is UUD. So as you saw before, U quark has +2/3 charge. So you have 2U quark, makes it +4/3, and a D quark having a charge -1/3, that makes it 3/3 and 1 electronic charge. Similarly, for neutron, you can see it is made of a U quark and 2 D quarks. So a U quark means you have a charge of 2/3 +2/3. D means -1/3. D again -1/3. So 2/3 -1/3 -1/3, that will be 0. and you know that neutron is electrically neutral or its charge is zero. Similarly, let's say you have a particle that is made of two quarks. Specifically, one of them is a quark, other one is an anti-quark. Those kind of particles are called mesons. You're not familiar with these particles. To name a few examples, you have pi mesons and phi meson. Pi meson is made of U, D, anti-D, and S anti-S. Phi meson is made of S anti-S. Now, do you have to remember this? Of course not. Not right now anyway. But you will get questions based on this once its example is discussed in this session. Next in this chapter is spontaneous radiation. You came across this topic in IG again. There are four basic type of radiations: alpha decay, beta decay, and there are two special cases of beta decay, beta minus and beta plus. And you have, of course, gamma decay. Now, an alpha particle is equivalent to helium nucleus. A beta minus particle is equivalent to an electron, beta plus a positron. Actually, this electron and positron are antiparticles of each other. And gamma particle is essentially a photon or light. Now, why do we have spontaneous radiation? I hope all of you know. An atom is trying to gain stability by releasing excess amount of energy that it has. And it is released in form of these decay process. Now, the question is, what happens to an atom? What change does it happen? What change does happen, obviously, apart from releasing energy? Are there any other change to its atomic number, mass number? Alpha decay, as I told you, it is helium nucleus essentially. So if from a nucleus, a helium nucleus is gone, then helium is to 4. So its atomic number has to reduce by 2 and mass number has to reduce by 4. We'll discuss example for this. For instance, let's say you have uranium 92 to 35. If it emits a helium nucleus or alpha particle to 4, okay, the daughter nuclei will have, which is essentially thorium, will have 92 minus 2, 90 protons, or its atomic number is going to be 90, and its mass number is going to be 231 because you lost 4 of it. And in these nuclear reactions, always remember to check whether the atomic number and mass number are conserved or not. Now in beta decay, as I told you, beta particle is an electron. So do we have electrons in the nucleus? We don't. So where do we get electrons from the nucleus is the question. How it happens is like this. Let's say we take a neutron, and a neutron is made of a U quark, a D quark, and another D quark. Okay. Now one of this D quark changes to a U quark. So one D is gone and you get a U. That makes 2U and a D. The particle is a proton. When a D quark is changed to a U quark and a neutron, it became proton. Now, let us look at it from a perspective of balancing this particular reaction. A neutron, it does not have any atomic number at all. And it has a mass number 1. It has charge 0. Okay. So it is electrically neutral. and it has a mass number equal to 1. Now, when you consider a proton, this has a positive charge, okay, and it contributes 1 to the mass number. As I told you, it is not electrically neutral, it has 1 positive charge. On the left hand side, you don't have any charge at all, it is electrically neutral. So on the right hand side, the total charge has to be 0. So you need an electron here, okay, which has a negative charge. Now you have a proton, you have an electron, so it is electrically neutral. Along with that, some other particle which we saw in the standard model, namely neutrino, specifically anti-neutrino here, will also be emitted. Okay, and this electron with a negative charge is what we call as beta particle, or this is beta decay. So what happens to a nucleus when beta decay occurs? Remember, we have a neutron, we lose a neutron and we gain a proton. Okay, so you're gaining a proton means your atomic number will increase by 1. Okay, and you lost a neutron, but on the other hand you gain the proton, which means the mass number will remain the same, or there is no change to the mass number. Similarly, if you consider beta plus decay, which as I told you is a positively charged electron or positron. For this to happen, you need a proton, and this proton has to somehow change to a neutron. Okay, now a proton is made of a U quark, another U quark, and a D quark, whereas neutron is made of 2 D quarks and an up quark. So one of this U has to change to D quark. When this happens, along with that, a positively charged electron will also be emitted. Let's see. As I told you, a proton is getting converted into neutron somehow. You don't have to worry about what is happening in the background, or how does it get converted, or whether mass is conserved in this equation. Those are questions that you can ask yourself later after the exam probably. Now you have a positively charged proton here. Neutron, as you know, it does not have any charge at all. So you need to have one particle with a positive charge, so that charge is conserved here, and that is your beta plus particle. Along with that, neutrino will be emitted. Okay, now these neutrino, okay, be that may beta minus decay or beta plus decay, antineutrino or neutrino, their energy will vary. Okay, they can have any value of energy. So you will see some questions related to this in paper 2. Now gamma decay is essentially photon or radiation in form of light. So when gamma decay occurs, there is no change to atomic number, or there is no change to mass number. To summarize these nuclear reaction, you have this table. You have alpha decay. The particle that is emitted is a helium nucleus having 2 positive charge, atomic number 2, mass number 4. Now, in general, if you write your parent nuclei to be X, A, Z, Z being atomic number, A being mass number, your daughter nuclei will have Z minus 2 atomic number and A minus 4 mass number. Along with that, you have alpha particle. So when you add this A minus 4 plus 4, you will get your A. When you add 2 plus Z minus 2, you will get your Z. Okay, so the nucleon number is conserved. If you look at beta decay, which is beta minus decay, you have a parent nuclei again, X, atomic number, Z, mass number, A. As I told you here, a neutron is getting converted into proton, which means your atomic number will rise by 1 and mass number will not change. And of course, along with that, you have a beta particle that has a charge equal to -1. Now, if you want to write for beta plus similarly, then instead of z plus 1, it should be z minus 1. And gamma decay is pure energy. There is no change to the parent nuclei, apart from the fact that it has less energy when gamma decay happens. We will discuss the properties of alpha, beta, and gamma radiation, and we will compare them based on its power of penetration, ionization, and how it can be deflected by a magnetic field. Now, alpha particle has lowest penetration power. It can be blocked by a piece of paper. Now, beta particle, on the other hand, can travel through metal of few millimeter thickness. If you want to really block gamma particle, which has the highest penetration power, apparently it has the highest kinetic energy as well. Now, if you want to block a gamma radiation or particle, you need to have concrete of several meter thickness or a lead line compartment. Now, based on ionization, ionization is the ability for a particle to create a charge separation in another atom in the vicinity. So it is possible for charged particles only. So here our charged particles are alpha and beta, and they can produce ionization of atoms. Now, a charged particle, when it moves, or basically let's say current, it experiences a force when it is placed in a magnetic field. Okay, so therefore, if alpha particle, beta particle, and gamma particle are subjected to a magnetic field, only alpha and beta will get deflected. And if they are going through the same magnetic field, they will move in the opposite direction. Now, gamma will be undeflected. Based on the topics that we have discussed today, let us analyze one question from March 21 paper. Okay, you're given alpha particle experiments and its two results. So the first result is that the vast majority of alpha particle pass straight through the metal foil or are deviated by small angles. Result 2, a very small minority of alpha particle is scattered through angles greater than 90 degrees. Okay, and we have to deduce conclusion or inference from these two results. So the conclusion that we can draw from result 1 is that atom is mostly empty. And as for result 2, we can conclude that mass is distributed in a very small region having positive charge. That is why you are getting a small deflection. A radioactive decay sequence contains 4 nuclei, P, Q, R, and S. Now, here you can see in the first part of the sequence, the atomic number getting reduced by 2 and mass number getting reduced by 4. So here it should have had an alpha decay. Now, look at the second step from Q to R. The mass number is remaining the same, and the atomic number is getting increased by 1. We have seen this in beta minus decay. Now, as for S, we don't know. So let us begin to the question. Nucleus S is an isotope of nucleus P. So isotope means that it has to have the same atomic number as that of P. So this has to be 84. Now, mass number has to be same as that of R. Have they mentioned it? They have not mentioned it. Mass number has to be 214 itself. Okay. Now, so proton number, you already know it is 84, and Nucleon number of nucleons or mass number, you have 214. Be very careful here. Sometimes they can ask you about number of neutrons. Now, as for the last question, the quark composition of nucleon Q changes as Q decays to form R. Okay, so remember what type of reaction was that? It involved an increase of atomic number, okay, and beta minus decay. And beta minus decay happens when a neutron changes to a proton, okay. So a U quark and two D quarks change to two U quarks and a D quark, okay. So describe this change to quark composition of nucleon. So you can say a D quark is changed to a U quark. And we'll discuss more questions from radioactivity in the following upcoming videos of this series. Thank you so much.